In this lesson, we are finding what is called a Riemann sum. A Riemann sum uses a graph to figure out area that is underneath a curve and above an x-axis. In calculus, the result of an integral of a function with respect to x, that represents the antiderivative of the function f of x. We sometimes call this an indefinite integral. We call it an indefinite integral because the D-E-F-I-N, that little bit, means defined. Is our function defined? And in this case, the defined portion of it is the boundaries. So the left and right boundaries. You will see, instead of just the integral of f of x with respect to x, you will see the integral from a to b of f of x with respect to x. So this guy is a definite integral. It's got definite starting and ending points. Indefinite integral, there are no starting and ending numbers. Okay. The result of this a to b integral of f of x dx is a value, a number. So you will be plugging in values for a and b that get plugged in for x. That value represents the area of the region bounded by the curve of f of x and the x-axis on the interval where x is between a and b. So let's take a look at the graph that is below to see what that actually means. We have an x-axis. That is down here, x-axis. We have a function. This is f of x. Okay, then we are given two other pieces of information. We are given that a is positive 1. We are given a is positive 1 and b is positive 7. So our goal is to figure out what is the area of all of this region. Now you guys have figured out areas of regions since like 6th grade probably, like a pre-algebra, that kind of a class, something in there. Or like a 7th grade math class. You guys have figured out areas of regions that are on graphs. What you do is you count up the areas of all the little squares. But hopefully you guys see the issue here. And the issue is that we have a curve instead of just straight lines. And this isn't like a really nice curve like a circle where you could figure out a radius and then use a circle area formula. We just don't have that. And because this is a curve, we have little pieces of boxes that are missing. So like here, there's a piece of a box that's missing. Here, there's a missing piece. Here, there's a tiny little extra piece. That extra piece kind of looks like if you rearrange it, it would fit in here almost. Okay, so we end up having to do like a lot of approximating, estimating what is the actual area. And Riemann sums are going to help us figure that out. They help us estimate the area under a curve. Later on in a future section, we're going to use antiderivatives to help us figure out the real, for sure, exact area. But this is a decent way to approximate. Okay, so bringing it back to like your 7th grade math, kind of what you did was you were like, all right, can I break this into shapes that I know how to find areas of? We're going to break this up into 3 rectangles. Our rectangles are going to have a width of 2 units. It says length, but really it's the width. It's how far like wide this way along the x-axis we're going. So on the x-axis, I'm going to break that up. From 1 to 3 is 2, from 3 to 5 is 2, and from 5 to 7 is 2 units. So we're going to make these rectangles come like all the way up, and then we're going to use the areas of the rectangles to approximate. We just have to know how high up to make the rectangles because we know that our widths are 2. We just need to know heights so we can find areas. What we're going to do is place the upper left-hand vertex of the rectangle on the curve each time we draw one of these rectangles. So between here and here, between my two fingers, the left side is over here. Okay. So I'm going to follow my left finger all the way up until I reach that f of x function, and then I'll draw across and then down. So this point is the one that we care about. That is the upper left-hand corner of that rectangle sitting on the curve of f of x. Okay. I'm going to do the same process for 3 to 5. Follow my left finger all the way up to get to the function. That's here. Go ahead and trace a little bit further down. Okay. And then from that point where 3 reaches that the function, you're going to draw straight across to the right with a width of 2, just like the bottom was, and then you draw straight down. Okay. Again, from 5 to 7, follow the left hand all the way up until you reach your curve. That is right here. You don't have to go up or down from there. Go to the side and then follow all the way down. So we're going to find the areas of those rectangles. Let's use blue. Areas of the rectangles. So that's going to be here. 1 rectangle, 2 rectangles, 3 rectangles. That's a pretty decent approximation. So all of the blue stuff and the green, right? Anything that I just highlighted with blue is what we are finding the area of. We can find areas of rectangles. Absolutely, we can. We just need to find the widths and the heights of those rectangles. The height of our first rectangle, I'm going to say rectangle 1, rectangle 2, and rectangle 3. The height of our first rectangle is going to be f of the x value, which is 1. Height equals f of 1. The width is 2. Our second rectangle, the height is going to be f of 3 because we were looking at the left-hand side to figure out how tall our rectangle should be. The height is f of 3, and our width again is 2. Rectangle 3, we followed from 5 all the way up, so the height is f of 5, and the width again is 2. We are given the function f of x equals negative 1/3 x squared plus 2x plus 5. So we can use the calculator to figure out those exact heights. I'm going to plug into y equals negative 1/3 x squared plus 2x plus 5. All right, just plug that into the y equals. And since we are plugging in whole numbers, I'm going to go to the table. Our first one was f of 1, and that is 6.6 repeating, so that's 6 2/3. So this height was 6 2/3. F of 3 is 8. So this rectangle had a height of 8. And x equals 5 was the other one. The height was 6.6 repeating again, so 6 2/3. So we've got 3 rectangles with 3 widths and heights. This rectangle is an area of 2 times, okay, let's see, 3 times 6 is 18, 19, 20. So that's 20 over 3. And this one's also 20 over 3. This is 2 times 20 over 3. This area is 2 times 8, and this area is 2 times 20 over 3. We can find each of those areas. This would be 40 over 3, 16, and 40 over 3. And then to find the whole area of everything that I've got as blue, you just add all three of them up. So that would be 16 plus 80 over 3, which is, calculator, 16 plus 80 over 3 is 42 and 2/3. Okay, so that is the area that is blue and green. Now you might be looking at that like, that is just not a very good approximation, and here's why. There's all this extra blue area that's outside of the region we care about. And then there's all this yellow area that we didn't include in our rectangles. I mean, it's not too bad, because if you take like this area and you kind of like rearrange it and shove it over here, it kind of fits in, but then there's still all this extra blue. So this is definitely a bigger number than the actual area, which was yellow to begin with. Okay, so maybe we could draw our rectangles a different way. Maybe instead of putting the left dot on the f of x, we could put the right side's dot on f of x. So we can just like make this rectangle taller so it fits like right there. Then this point would kind of shove down to here, and this point would shove down to here. Let's see if that helps. So go ahead and, so sometimes that works. Sometimes it works better to make your rectangles skinnier. Sometimes it helps to do a different shape. Let's start by making our rectangles skinnier so that like this rectangle bloop, goes to here, and then this rectangle has a height that goes all the way up to here. That's pretty good. Let's try that. Okay, I'm gonna go ahead and draw out from 1 to 7, and then here was our x-axis, and then here's our function. Okay, so that's the area that we actually do care about. I'm gonna make it yellow again. Beautiful. Just called my own work beautiful, whatever. All right, now we are doing a subdivision. So we're dividing into little subsections, dividing that area bounded by the graph of the function. Boundaries, they're boundaries. That's what bounded means. The rectangles have length 1 unit. So from 1 to 2 is gonna be a rectangle, 2 to 3, 3 to 4, and so on. Those are those widths. We are again doing a left-handed Riemann sum. So we're going to take, for this first rectangle, we're gonna take the left finger and go all the way up until we reach our function. And then that's going to be the height. Okay, we're only going over a width of 1 this time, and then moving back down. Okay, now for 2, from 2 to 3, follow your left hand up until you reach your function. And then go straight across, and then down. From 3 to 4, follow your finger all the way up from the 3, from the left-hand side, till you reach your function. Go across, and then down. From 4 to 5, follow all the way up. Ooh, it's a little shorter this time. To the right one, and then all the way down. 5 to 6, ooh, I almost did both. Follow the left hand up till you reach the function, and then all the way down. And we got one more. Between 6 and 7, here, to the right, all the way down. So this time our rectangles, this is the actual area that we are finding when we find the areas of our rectangles. There's a tiny little bit right there. Wow, I would have failed kindergarten coloring right there. We can see that there's less yellow space on this example than there was in the first time we had this drawing. I guess I'll zoom out a little so you can see them both. This was the first drawing and this is the new one. So there's less yellow space, and it looks like there's also less blue space, because like this piece was blue, and then from here all the way over to here, this was also blue. So if we're minimizing the amount that's not used under the curve and minimizing the amount that is outside of the curve, we're going to get a better and better approximation. Okay. So we have 1, 2, 3, 4, 5, 6 rectangles this time. All of them have a width of 1. Rectangle 1, rectangle 2, rectangle 3, 4, 5, and 6. All have a width of 1. And their heights are all different. So they are still, heights are f of 1, okay, because we're looking at the left-hand side. That's how high that is. R2 is f of 2. R3 is f of 3. R4, f of 4. F of 5, and f of 6, okay? And again, it's just because like that's the left-hand side of this interval. That's how tall the rectangle is, because the left-hand corner touches the function. It has nothing to do with the fact that that's rectangle 1 and that's a 1. Okay. So we got to figure out those f of numbers, and luckily we had a table. We figured this out earlier. So f of 1, all those 0.6s, that's a 2/3. So 6.6 repeating is 6 2/3. F of 2 is 7 2/3. 3 gives us 8. That's 7 2/3 again. This is a parabola, so it has a mirror image. 6 2/3. And then f of 6 is 5. Okay, so these are our heights and these are our widths. To find areas, you are going to multiply the width times the height. Hopefully it's pretty obvious that we're multiplying by 1 every single time, so our heights are also going to match our areas. So these widths of 1 are a pretty good idea. I'm going to go ahead and rewrite the areas as the fractions over 3. This was what, 20? Yep, 20. So this would be 23. 3 times 3 is 9. 23 and 20. So 6 2/3 times 1 is 20 over 3. These are the areas of all the different rectangles, and when you add them all up, you get the area of all of the rectangles combined. So I'm going to add all those numerators because they have the same denominator. So 20 plus 23 plus 9 plus 23 plus 20 plus 15 is 110 over 3. That is not divisible. This is 36 2/3. Okay, that is a little bit less than the first time we did this, and we got 42 2/3. So there's less extra junk. So we are getting closer and closer to the correct number. Now we can do this again with width of a half. I'm going to help us set that up a little bit, but we're not going to do the whole thing because I think we're probably getting the hang of it. So we would have from 1 to 7, we would have 2 times 7 is 14 rectangles, right? A half, 1, a half, 1, a half, 1. There are 14 rectangles with width equals 1/2. Okay, so we need to find all of the heights. The heights are going to be like f of 1, f of 1.5, f of 2, f of 2.5, and so on. I'm going to do dots for and so on. All the way until we get to f of 6.5, because that'll be the last rectangle, whoop, all the way up to here. It's a terrible line. because the left side of the rectangle is going to be at 6.5. The right side is at 7, at x equals 7. So that has to be the left. Okay, let's use this space to talk about how we can make this work easier for us, because this is a lot of junk. That's a lot of writing. You might notice that all of our rectangles had the same width in this example and the previous example, and then in the 1/2 example. So if we're finding areas of rectangles, what if we undistributed, we factored out the width? So the area would be 1 times the heights. In our very first approximation, they're numbered. So this is approximation number 2. And approximation number 1, our area would have been 2 times. And then we had 3 rectangles. So we would need 3 different heights. And those would be like f of 1, f of 3, and f of 5. We just factored out a 2. Because why should you multiply by 2 3 different times? That is a waste of time and effort. Just add up all of your heights, so 20 over 3 plus 8 plus 20 over 3, and then multiply by 2, and you still get the same answer. That's what makes distributing and factoring so awesome. All right. The next set of things we are going to do is the right-hand Riemann sum. This one is a length of 2 units, so this is page 482 in your notes. All right, we're still trying to find that same yellow area between 1 and 7, between the x-axis and our function f of x. We're told that our length is 2 units, so let's go ahead and divide those into 3 different rectangles, width of 2. And then instead of moving the left hand up, you're going to move the right hand up. So between 1 and 3, 3 is your right hand, move it all the way up till you get to here. And then you're going to move left and then move down, drawing as you go. Oh, I forgot to do yellow. Okay, second rectangle between 3 and 5. The 5 is going to move up until we get to this spot right here. So that's the height. And then straight across, and well, we don't really have to draw down because we already have that line drawn. Okay, third rectangle, 5 to 7. Move that 7 finger up till you get to the function. Ooh, that stops right there. Draw to the left. Now I'm going to do blue for those areas of the rectangles, which of course makes some pieces green, like the overlaps. So you can see this blue area up here is area that we are including in our rectangle area that is not actually in the area that we're looking at. And then this area and this area that are yellow are supposed to be included, but they're not. Since the blue area is definitely smaller than the yellow area, this is going to be an under approximation. The rectangles don't fill up as much area as the actual curve. All right, let's use that newfound area method. So this is going to be area equals, the width is 2 of all those rectangles, and then we have 3 rectangles. So we need to find the 3 heights. Remember that we are using the right-hand side this time, so it's not going to be exactly like what we did on the very first approximation. We are going to have f of, and f of for those heights. Our first rectangle, we use the right-hand side, so that would be f of 3. Our second rectangle, we use the right-hand side, so that's f of 5. And our third rectangle, we use the right-hand side, so that's f of 7. And hopefully we notice that the difference between 3 and 5 is 2. The difference between 5 and 7 is 2, because that's the widths of our rectangles. Okay, f of 3 is up here, f of 5 is up here, and f of 7 is up here. We can again find those using our calculator. If you've got that table, you've already got your numbers. F of 3 was 8, f of 5 is 6 2/3, f of 7 is 2 2/3. So this is 2 times 8 plus 6 2/3 was 20/3. And then 2 2/3 is 6, 7, 8/3. Okay. From here, you can add up all of your insides and then multiply by 2. Don't distribute. That's a waste of time. All right. 8 plus 20/3 plus 8/3. 8/3 is 24. 24 plus 20 plus 8 is 52/3. Right, 24 plus 20 plus 8, yeah, 52/3. And then multiply that times 2 is 34.6 repeating, so it's 34 2/3. Yay. Okay, we should notice that 34 2/3 is below what we got for the first one, which was 42 2/3. This was an over approximation. This one was an under approximation. Okay, we can do the same thing with the right-hand Riemann sums. I'm going to go ahead and let you do that one if you want to. And same thing with approximation 6, which has length 1/2. All right. So before we continue, what inference can you make about the approximations as the lengths of the rectangle decreases? The length of the rectangle decrease. Boop. Grammar. Okay, as the rectangles get skinnier, we get a better and better approximation. And graphically, this is because we have less extra area above or below f of x, right? Less blue area and less yellow area. We want it all to be green. We want the rectangles to include every single thing that is yellow. Okay, and those, like drawing out all of these guys. I know I'm not making you do it, but I'm going to do it. Drawing out all of these little guys. There's so little extra area that it's kind of hard to draw. Like when you get closer and closer to the correct amount, harder and harder to draw. I should totally have used a ruler. And I would say lesson learned, but I've done this like 8,000 times. Okay, there's a tiny bit of yellow area here and here. And all of these little guys have tiny bits of blue area. Okay, there's less area that is included in the rectangles that is not included in the area itself. More overlap between actual area and rectangle areas. I don't know. You can word that however you want. Okay, moving on to the next page. The next thing we're going to do is called midpoint Riemann sums. These get a little bit more complicated. We're doing the same basic principle. But this time, instead of doing the left side or the right side, you have to find halfway between the left and the right side. We are again doing length of 2 units for our rectangles. So draw this guy out, do our length of 2 units. All right. Now, our rectangles, instead of moving our left hand up or our right hand up, we're going to meet them in the middle. So halfway between 1 and 3 is 2. So we're going to take this 2, and I'm going to use my red, pinkish color, and I'm going to trace this all the way up until I get to our function. And that is going to be the height. So you find the midpoint between these two x values, 2, and then trace that all the way up. You don't have to draw this, but at least follow along. And then you have to draw the left and the right sides. I guess it's kind of hard to see that this is pink. Anyway, between 3 and 5, halfway between is a 4. So we're going to follow this guy up until we get to our function and make that the height. And then you follow down. Okay, from 5 and 6, halfway between, 5 and 7, halfway between is 6. There's f of 6. So this is our height. And then followed down on the sides. So our 3 heights are f of 2, f of 4, and f of 6, instead of those odd numbers from the edges of our rectangles. The widths of the rectangles are 2, or the lengths, whatever. This way is 2, and then the heights there are the y values of the midpoints. So that's going to be the area of all of the blue stuff. Let's do blue now. So green is the area that is actually underneath and inside the rectangles. Okay, and this is, oh my goodness, so much better. You can see this little yellow area up here that's not very big, but the blue area, that's still fairly small. And then this yellow and this blue area are pretty darn close to each other. So they kind of cancel each other out. So this is probably the closest we've had so far. Let's figure out f of 2, f of 4, and f of 6. We figured that out earlier. So f of 6 was 15 over 3. It's 5, just 15 over 3. F of 4 was 23 over 3. And f of 2 was also 23 over 3. So we can add those 3 things up and then multiply them by 2 and get the whole area. Okay, 23 times 2 plus 15 is 61 over 3. So 2 times 61 over 3 is going to be 40 and 2/3. That's our best one yet. If our intervals have a length of 1 unit, so this same deal. If our rectangles have a length of 1 unit, then halfway between them is like 1.5. So that's not that pretty. But you do the exact same thing. Halfway between 2 and 3 is 2.5, which is here, height, here, height. Between 4 and 5 is 4.5. Here. 6. And then between 6 and 7 is 6.5. Okay, so all of those heights would be like f of 1.5 plus f of 2.5 plus f of 3.5 plus dot, 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 f of 6.5. When you write them out, you should write all of them when you're actually doing these problems. So that's going to be the sum of your heights, and then you have to multiply times the widths. The width of each rectangle is not a half. The width of your rectangles is 1. Okay, which that should make sense because between this x value and this x value, that is a difference of 1. Okay, and of course, we're getting closer and closer to having the perfect overlap between the rectangles and the actual area. Next page. The next thing we're going to do is called trapezoidal Riemann sums. I'm going to go ahead and pause us now and make a second video of that.